Welcome everyone to another session on a video lecture on Physics 1. Okay, today's discussion is on Newton's laws of motion, and the coverage would be the following topics: Aristotle's and Galileo's ideas on motion, Newton's first law of motion, forces in Newtonian mechanics, free body diagram, Newton's second law of motion, systems in translational equilibrium, systems in non-equilibrium, friction, and finally Newton's third law of motion. Okay, to start off, we start with the ideas of motion of Aristotle. Of course, you know Aristotle. Aristotle is a Greek ancient philosopher, and his ideas of motion is basically of two types, which is the natural motion and the violent motion. Natural motion is the one that he uses to describe the natural tendency of objects to seek their natural place in the universe. How does this work? Basically, for Aristotle, every object in the universe is made up of basic elements. These elements are earth, air, water, fire, wood, and metal. So, every object is made up of one or two combinations of these elements. So, for example, a stone is made up of earth. Smoke, for example, from a fireplace is made up of air. And feather, for example, for Aristotle, is made up of one part earth and one part air. Now, this basic composition of all matter dictates the natural tendency of all objects to seek their natural place in the universe. So, for example, you have a stone on top of a cliff. The natural tendency of the stone on top of the cliff is for the stone to slide down the cliff, seeking the lowest possible position on the surface of the earth, because basically the stone is made up of earth. Now, smoke, of course, rises basically because it seeks its natural resting place or its natural tendency to be merged with the air in the atmosphere, because smoke is basically made up of air. And another example is for feather. A feather for Aristotle is made up of one part earth and one part air, but the more predominant composition is basically earth. So for Aristotle, a feather would actually fall towards the earth because of its major composition of earth, but it actually falls slower because of its composition of air. Now, Aristotle's explanation of the natural motion of an object is basically based on observation and not on experimentation. As we are going to see later on, as opposed to the ideas of Aristotle, Galileo Galilei will be having his own explanation of motion, but basically based on the combination of observation and experiment. Okay, so for Aristotle, this is called the motion of the stone, the feather, and the smoke is basically examples for natural motion. Also, included in the natural motion of Aristotle's idea are the motion of the celestial objects, for example, the motion of the moon and the stars. So, for Aristotle, the natural tendency of the moon is to revolve around the earth, just like the other stars, as we observe it from our perspective as observers on top of the surface of the earth. So for Aristotle, you do not need actually any type of tendency or force to keep the moon moving around the earth. It is simply because it is the natural tendency of the moon to revolve around the earth. It's just natural. The second type of motion based on Aristotle's idea is called violent motion or imposed motion. Imposed motion is basically results in by the application of a push or a pull on an object. So, for example, if you have a ball, and in order for you to have the ball rolling, you need to apply a pushing force in order to start off the motion of the ball. So another example, if you have a cart, so in order to start the movement of the cart, you could either push the cart or pull the cart. So in all these examples, Aristotle's explanation is that these are called imposed motion or violent motion. Now let's go to the ideas of Galileo regarding motion. Okay, so Galileo was credited for demolishing the ideas of Aristotle that a force is needed in order to keep things moving. He based this idea on not only on observations but also in experiment. Galileo was dubbed that there is a force that occurs between two surfaces, and he called this force the force of friction. And the frictional force is the type of force attributed to the tendency of an object to slow down and eventually stop, such as in the example of a rolling ball. We know by observation that if you roll a ball, for example, a basketball on top of the surface of the basketball court, natural observation would dictate that when you roll a ball, we see the ball eventually slows down and eventually stops. Galileo explains this phenomena by uh, introducing the idea of friction, that there is friction that occurs between the surface of the ball and the surface of the basketball court, and this friction is the one who causes the ball to slow down and eventually stops. Also, in extension, if if we are able to eliminate entirely the effects of friction, what happens to the motion of the basketball is that the basketball would actually continue moving without slowing down, without speeding up, without changing direction, for as long as we can eliminate friction, and for as long as the ball would not encounter any obstruction along the way. This theory of Galileo regarding the regarding motion was actually verified by astronauts when astronauts went outer space. And of course, in outer space, you have a vacuum as your environment. A vacuum is a place where air was actually evacuated, so there is no air. So, meaning, if you're going to throw an object within this environment, such as outer space, the object will not encounter any opposing forces or frictional forces from the air. So the natural tendency of the object is for the object to continue moving in a straight line direction without slowing down, without speeding up, and without changing direction. For as long as the object would not encounter any obstruction, no object will hit our object. The natural tendency of the object is to move in a straight line motion without speeding up, without slowing down, and without changing direction. It would continue moving with a constant velocity. It follows, and this implies, that you do not need a force in order to keep things moving. So we see here that the ideas of Aristotle, as opposed to the ideas of Galileo, they are in direct substitution. For Aristotle, you need a force in order for an object to move in a straight line direction or in a given direction. Whereas for Galileo, you do not need this force. Okay, so between the ideas of Aristotle and Galileo, which among these explanation or ideas are the ones that we are actually accepted today? Of course, today we accept the ideas of Galileo in order to explain the movements of any object. So the the advantage of Galileo's ideas is that Galileo's ideas are based on experiments and not merely on observations, as opposed to the ideas of Aristotle. Okay, so we now move on to the more general accepted views of motion, particularly the views of Isaac Newton. Of course, we attribute the laws of motion to Isaac Newton. His three laws of motion are called the first law, the second law, and the third law. Correspondingly, the first law is called the law of inertia. The second law is called the law of acceleration, and the third law is called the law of interaction. So we'll be going through each of these laws of motion one by one. Okay, so let's start with Newton's first law of motion, and this law of motion is called the law of inertia. Okay, this is the basic statement of the law of inertia. An object at constant velocity remains at its constant velocity unless an outside unbalanced force acts on it. Or, if you recall Newton's first law in your high school, Newton's first law is basically stated in this form. An object at rest tends to remain at rest. An object in motion tends to remain in motion. The second part, the statement of Newton's first law, in the second form, is basically composed of two parts. One is an object at rest tends to remain at rest, and the second part is an object in motion tends to remain in motion. The second part of the second form of the statement of Newton's first law is actually the same idea as presented here in the slide. An object moving at constant velocity remains at its constant velocity unless an outside unbalanced force acts on it. But in the more general sense, constant velocity is basically since velocity is composed of speed and direction, constant velocity means you are maintaining the values for the speed and its direction. So it could be that the velocity has a non-zero value. It could also be that the velocity has a zero value, both of which could be possibly could be maintained as a constant velocity. So in a general sense, an object that has this tendency to maintain its constant velocity maintains this constant velocity by natural tendency unless an outside unbalanced force acts on it. And we call this tendency, or Newton called this tendency of object to remain at rest or to remain in motion, he called this inertia. Of course, inertia, although it's possible that you are not familiar with the term, but we observe inertia every day in our everyday lives. So, for example, we observe inertia whenever we are riding on a car or on a jeep. Try to notice that when you are on the jeep, and initially that the jeep is at rest, and you are inside the jeep. Now, for when the scenario is that when the jeep starts to move, what happens to your body if for example the jeep started to move towards the left? The natural tendency of your body is that your body will actually be moving towards the right momentarily. This phenomena is called inertia. And why is it that your body moves towards the right whenever the jeep moves towards the left? Uh, Newton's ideas on inertia is actually equivalent to the notion of mass of an object. And these two are actually directly proportional. The greater the mass of an object, the greater the inertia of an object. And inertia for Newton is a natural property of any object. So how does this property work? Inertia remember in our statement of Newton's first law, inertia refers to the natural tendency of an object to seek its original state of motion of being at rest, or either being at rest or being with constant velocity. So what does this mean? This means that if an object is already at rest, the natural tendency of this object is to maintain its state of being at rest. Now, of course, in opposition, if an object is already moving, the natural tendency of an object is to maintain this constant velocity when it is already in motion, or when it is already moving. Now, we refer to this natural tendency, we refer to this as inertia, and inertia works such as in our example, in our Jeep example, when the Jeep moves towards the left, your body actually seeks its natural tendency of being at rest momentarily, until such time that the motion of your body was overcome by the dragging effects of the motion of the jeep. So our body moves towards the right when the jeep moves towards the left, simply because the inertia of our body tends to seek the original state of motion of our body of being at rest. Now, let's take on another scenario. So, for example, we have the jeep scenario again, but this time the jeep is already moving, and you're inside the jeep, moving along the direction of the jeep. Now, what happens is, if the jeep suddenly stops, what happens to your body is that if the jeep is moving towards the left, and the jeep eventually stops, what happens to your body is that your body continues moving towards the direction of the original motion, which is moving towards the left. And again, what this phenomena is, that we usually every day observe, is called inertia. What happens to this second scenario is that, by virtue of inertia, your body seeks to maintain its original state of motion of moving towards the left. When the jeep suddenly stops, what happens to your body is that your inertia takes over, and your inertia tends to maintain the motion of your body of moving towards the left. And again, we call this natural tendency as inertia. Okay, what is inertia? Inertia is the tendency of an object to maintain its original state of motion, whether the motion is at rest or moving. Of course, as mentioned a while ago, the inertia of an object depends on the mass of an object, so it follows heavier objects possess more inertia than lighter ones. This means that the heavier an object is, the more its tendency to maintain its natural state of motion. So, for example, if you have a concrete wall, and a concrete wall has a great mass, therefore it has a great value for its inertia. It has a greater tendency of maintaining its natural state of motion of being at rest. That is why it is hard for us to push against the concrete wall. It is hard for us to topple down the wall, because basically of its large amount of inertia. Okay, so let me introduce to you the ideas of weight. Remember, weight and mass are two different things. Weight is a type of force, and basically the weight of an object is the pull of the Earth's gravity on an object, while mass is actually refers refers to interchangeably with inertia. Sometimes in physics we refer to mass as inertia, or we interchange the ideas of mass with inertia. And inertia is a property of an object, while weight is considered as a force. And weight is basically the pull of the Earth's gravity on an object, or the pull of gravity of a planet on an object. And this is the weight of an object is basically obtained by multiplying the mass of an object multiplied by the acceleration due to gravity of the Earth. Okay, so the acceleration due to gravity of the Earth is considered a constant on places near the surface of the Earth, and this value has the value 9.8 meter per second square. Okay, so in our formula we have F sub W, or the force or the weight of an object, is equal to mass times G. So therefore the weight is different from the mass. Otherwise, if they are the same, then we will not be having this formula. It follows by conclusion, or by implication, that mass is different from the weight. Now, in terms of complexity of examples, let's take let's focus on the idea of mass. Mass is basically the composition of how much matter is made up in a body. So, for example, if a body has 50 kilograms for its mass, if you move the body on top of the mountain of Mount Everest, if the 50 kilogram object is 50 kilograms on the surface of the Earth, and you move that object on top of Mount Everest, the amount of the mass of the object does not change. Also, if you move that object on the surface of the moon, if it is 50 kilograms on the surface of the Earth, on the surface of the moon it would still be 50 kilograms. Now, on the other hand, the weight of an object, it depends on the planet on which the object is on. So, for example, the object is on top of the Earth, and the weight of an object on top of the Earth, for example, is say 120 pounds. When the object is moved, for example, on the surface of the moon, where on the surface of the moon the force of gravity is actually weaker, therefore the force of gravity of the on the 120 pounds on the Earth would be actually lesser on the surface of the moon. And the surface of on the surface of the moon, the force of gravity is actually 1/3 weaker as compared to the surface of the Earth. Therefore, the original weight of the object, which is on the surface of the Earth, which is 120 pounds, on the surface of the moon, this would actually be 30 pounds only. So simply because of the moon's weaker gravitational effects on the object. Of course, the force of gravity is always directed towards the center of the planet, or towards the center of the Earth. If you're on the Earth, if you're on the moon, the direction of gravity of the moon is towards the center of the moon. Now, at this point of the discussion, I am actually introducing to you several types of forces that we will encounter later on. So I have already presented to you the gravitational force, which is the weight of an object. Next in our discussion is the normal force. Okay, so what is the normal force? The normal force is actually the support force, which supports an object if the object is on top of a given surface. So, for example, you have a block here on top of the table, and if you're going to analyze what are the forces that are acting on the block, naturally, the block has its own weight. Therefore, and since the weight of an object is the force of gravity on the object, and the force of gravity is always directed towards the downward direction, towards the center of the Earth. Now, of course, since the block is resting on top of the on top of the table, therefore there should be a support force provided by the table in order to support the weight of the block. We call this support force provided by the table the normal force. Of course, in this idea, the normal force is the support force provided by the table in order to support the weight of the block, in opposition to the gravitational force or the weight of the block. So if we're going to draw these two forces, the force of gravity and the normal force, in a free body diagram or in a Cartesian coordinate system, the normal force would be directed towards the positive y, and the weight would be directed towards the negative y. Okay, so the normal force is, of course, is a type of force that is called a contact force. Contact force is a type of force that acts between two objects that are in contact with each other. So in our example for the block and the table, it is necessary for the block to support the weight of the in order for the table to support the weight of block, the block and the table should be in contact with each other. Now, the normal force here, the normal refers to perpendicular. So, in terms of direction, the direction of the normal force is always a force that is acting perpendicular to the surface of contact. So, for example, the surface of contact between the block and the table is within the direction of the surface between them. Perpendicular to this surface would be the direction of the normal force. Okay, so in this illustration of a boy pushing against the rock on top of the surface of the ground, there is actually two normal forces here. One is the support force provided by the ground on the weight of the rock, and another one is the normal force provided by the exerted by the boy uh, on the rock towards this direction. Of course, the direction of the normal force is in between the surface of contact between the surface of the stone or the rock and the surface of the hand of the boy. Now, of course, since this is the direction of contact, the direction of the normal force would be perpendicular to this direction. Okay, so next in our discussion would be the type of force we call the tension. So what is this type of force? The tension is a force that is transmitted through a string or cord or a cable when it is pulled tight by forces acting from opposite ends. So for example, you have a suspended chandelier here in this illustration. The tension of on the cable that supports the chandelier is actually the force that exists within this cable. And the idea of the tension is that the tension provides the support force which counters the effect of the weight which is acting downwards. So of course, in order for the tension to support the weight is always downward. The tension should be acting towards the opposite direction, going upward. The string must be stretched to the point that it runs straight before it can exert tension. Otherwise, if the string is not fully stretched, it would not be able to do its effect on supporting the whatever weight is suspended on its end. Okay, so the next one is friction. Just like what I have presented to you a while ago on the ideas of motion of Galileo, it was introduced in that discussion the idea of friction. So what is friction again? Friction is a type of force that resists sliding motion. It acts parallel to the contact surface of contact. Two conditions in order to have friction between two objects. Objects must have surfaces in contact, and objects must be sliding along the surface of contact, or at least there must be an external force that is trying to slide the object. Now, these two type of contact or application of the frictional force corresponds to a different amount of force amount of frictional forces depending on the materials that are in contact. So for example, you have two surfaces such as rubber and cement, such as when you have the rubber tires of a car in contact with the cemented pavement. So the amount of frictional force that exists between the two, the surface of rubber and the surface of cement, depends on whether the two surfaces are sliding over each other or simply rolling over each other, or when simply when the rubber is resting on top of the surface of the cement. Now, this type of friction that exists between these uh, three scenarios, corresponds to different amounts of forces and different types of frictional forces. And these two types of forces, we call them static friction and kinetic friction. When the rubber surface is simply resting on top of the cement, such as when the car is at rest on top of the pavement, we call the type of friction that exists between the rubber and the cement, we call it static friction. But once that the car started to move, the type of friction that exists between the surfaces is no longer static but kinetic. So we call this kinetic friction. Now, to illustrate that, so whenever you have an object that is simply resting on top of a given surface, there are no outside forces trying to slide the object horizontally. Hence, there will be no friction other than static friction. Now, of course, static friction depends on the weight of the object and the normal force that counters the effect of the weight of the object. Of course, this means that the greater the weight of the object and the greater the surface in contact, the greater the static friction. Later on, we will be dealing more of this in detail. Okay, so this scenario is that whenever instead of having static friction, you have kinetic friction, and this is the scenario goes whenever you have forces that causes the object to slide across the surface of contact between the object on top of the surface that supports that object. An outside force F is trying to slide the object. Static friction prevents it from sliding. The magnitude of that force equals the force of the static friction. Once the object starts moving, it is no longer static friction but kinetic friction. Just like what we see here. Okay, so